doing? Little cold? You put the card in. So there's a little problem with uploading the videos online. I just put the one from Tuesday, and this one might take 2-3 days. So don't expect it by tomorrow, that's what I'm saying. So what did we do? We said we'll put it somewhere in here maybe. We had example number 1 was fractional knapsack. That was saying given a bunch of items, so there was a Z that was the capacity of the knapsack. There was an array of what do you call it, weights. Let's say those are the array W. And there was the array of values. So the task was select quantities QIs, right? That are smaller than weight I. So for each item like coffee or sugar, I could take at most that. What was another constraint? The sum of the quantities I select has to be Z, and I want to maximize the what?
Value.
Right, so how do I write that? Is the sum over the items, right? To be the quantity I choose of each item times the value or totals, right? So value divided by weight. Right? If this was the coffee, that was the price ratio, times how much I get, I want to maximize it subject to those constraints. In optimization, those will be called constraints, and that's going to be called objective. This is the objective, these are constraints. Good. And we solved this problem. We figured, is there a way to do it greedy, right? Okay? So then, what was the other example we just started? Activity selection. Let's write that one down. Problem. I think it's called ASP. Problem. They were saying I have a set of activities with start time, let's call that S, and finish time, F. Of course, each S of I has to be smaller than the F of I. And I have a time interval. Say it starts from 0 to max, something like that. It's like 6 a.m. to 12 at night or something. And what was the problem here? We want to select activities. And here when we say select, this QI is not a binary thing, right? It's not a choose it or not choose it. So QI, it can be between 1 and 0. Not between 1, between WI. So allow partial, right? There's a version of this problem where QI is not partial. You either take the painting or you leave it. In here, it's binary. So when we say select activities, we want to know which ones. We can call it QI again. QI in here belongs to. So you either choose your activity or not. Right? What do we want? The constraint is that there's no overlap. If IJs are selected, so say QI and QJs are both selected, then either the finishing time of I is smaller than the starting time of J, or the finishing time of J is time of I. So it's saying that if you select two activities, I and J, they can't overlap. Right? One has to start after the other one finishes. That's the constraint. What was the objective? Maximize the count. We can write that as sum of QIs, right? Because the QIs are 0, 1. And you guys, after a few trials, came up with an idea here that worked? What was the idea? Somebody, hands up, one person. Yes?
Earliest end time.
Earliest?
End time.
Earliest and time. So the greedy choice is choose activity, select activity, with earliest finish. How do we write that mathematically? Minimum of Fi, right? And we'll have to, of course, eliminate overlapping activities. Once I pick that activity, anything that's overlapping with it, it's not valid anymore. In greedy is characterized by the fact that when I make a choice, I don't go back and revise it. Somehow that choice has to be good. So once I choose an activity, here, I choose this one, I'll have to eliminate the other two because they overlap with that one, they're not allowed. All right, we can solve this problem, and we will. We said another few things that were important. One was that greedy algorithms are fast. It's very little, you still have to show it, but it's very little doubt that if you have an algorithm that makes a greedy choice, that's going to be an efficient algorithm. That's not the worry here. What is the worry for greedy algorithms? What is the main problem that you have to worry about?
It's not optimal.
It's not optimal. That's the biggest problem. Because the greedy choice makes it efficient, right? I pick the one that has a certain property, in this case, earliest finishing time, and if that's good, moving on, it's easy after that. The problem is, how do I know I'm going to get an optimal solution? So this is usually efficient. If you could run a greedy algorithm of a problem, it probably means that's a very good algorithm. The question is efficiency. So we're going to solve this problem. What does it mean to solve it? I mean, writing pseudocode for greedy, that's another thing. Usually efficient. Let's write another property. A pseudocode easy. It's not like I'm saying don't write it. You're gonna have to write the pseudocode. But in greedy, if I decide on a greedy algorithm, the pseudocode is gonna be pretty simple, right? Choose that activity, right? Then what? Eliminate the ones that are blocked by it, and then repeat, right? Choose the next activity with the earliest finishing time, put it in, select it, block the activities that are overlapping with that one, repeat, right? Usually, it's efficient and it's not hard to write the pseudocode. Now, you should still write it. Let's try to do that. Let's try to write the pseudocode right here. So maybe I should sort those things first. Huh? How should I sort them by? Okay, so sort, let's say the pseudocode here, activity selection problem with that input. Say this are the start arrays and the finish array. I'm going to ignore the max thingy. I'm going to assume my time is all the time in the world for simplicity. It's not hard to eliminate all activities that don't fit in here. If the earliest time is smaller than 0, eliminate. If the finishing time is bigger than max, eliminate, and then you don't have a time constraint. So then what would you say? We sort first, sort by increasing by f, right? Sort by increasing f, and then loop, right? Is a loop here. We choose the activity with the smallest f, finishing time. Then how do I eliminate all activities that overlap with it? So let's think about if this sorting helps me at all or not. So I've got this sorting. How they look? This one finishes first, right? Now the second one can start earlier or after, but it has to finish after. So maybe the second one is here. The third one can start here, but it has to finish after, right? Look at the finishing time, they have to be sorted, right? So at some point, I choose an activity, that's this one, right? Here, that's my current one. So currently selected. I just selected this activity. That's the one I selected here. When I say choose the activity of the smallest f, I choose that one at this point. Which are the ones that have to go out? So, do I have to worry about the ones before? If I got to this point, somehow I'm done with that part already, right? Either I selected something or they were blocked by other activities and somehow it's done, right? Because if one of those will still be available, I would have chosen that one, right? By the minimum finishing time. So this is not a concern. I'm not worried about that part. So how is the next activity going to look like? The ones that are still in play. It has to finish after it, right? It may start either after or it may start before, right? So now, which ones need to be eliminated? The ones that have this start time before the finish time. So I have to go, they're sorted already. I'm going from here and I say eliminate, 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 right? So I'll have to go what? This is the activity, say this is the activity J. I'll start for T equal with, which is the first activity I need to, this is J. From J plus 1, right? From J plus 1 down, right? I don't have space here, but I'll try. So when do I take it out? If start time of T is smaller than Finish time of j, delete or block, right? Delete. I don't like the word delete because it's overloaded means something. You say block that activity. Now, as an exercise for you guys, this is obviously what we need to do. We need to go from here. This is j plus 1, j plus 2, and we need to go down up to, we see 1, up to where actually? How far do we need to go? Can I say, once I see an activity that starts after this, say there's an activity here, if it starts after, that's still valid, right? So this remains valid, not blocked. Can I stop right here?
No. You can.
I think we should be careful here. Here's the problem. If I keep going for everyone I select all the way down, what kind of algorithm running time I'm going to get? If for any n I have to go down, in principle it could be n squared. I don't think it's n squared. I think this can be done faster than n squared overall. So I don't want to do it now because I want you guys to think about it. And as a fair warning, friendly warning, there's some version of activity selection problem in 50% of the midterms. So looking at the past 10 years, there's some variation of this in the midterm. Sometimes it's a problem, sometimes it's a question. How many activities need to be blocked every time I do that? Overall, is that an n squared time algorithm? This kind of question or variation of it happens about every once in 2 years in the midterm. So my thinking here is that sounds good. If I go n squared and eliminate those activities, obviously that's going to be correct. But once I eliminate, I see this one. What should I do here? Maybe I could just select this one. Can I just put it in, say that's a good one? And then, can I just keep moving somehow? So I don't have to do n squared. I'm not saying that's true. I'm saying, why don't you go home and think about this problem? So while the greedy choice, I think it's very little doubt that's correct. We're going to prove that in class right now. How would you actually implement this algorithm in terms of the runtime, right? Is it n squared, n log? Actually, there is an n log n just from the sort, right? If you sort, it's n log n. So I think we should, from the beginning, assume n log n is okay if I start with a sort problem. There's another question, can you do it faster than n log n? That would mean you can't even sort. But let's assume you sort. Now, can you do it in n log n time? And this will be n squared, at least grossly approximated. Maybe it's not really n squared if you're careful. Okay. So what we have to do here is, I'm going back to my main theory from last time. That's an exercise for you. So here, this is incomplete. I mean, that's the idea, but how do we actually do it? Maybe we need some fancy data structure that somehow once we pick this activity, we already know somehow that the ones before it, the ones that's more or less are blocked. I don't know. So what did we say? Here's the divide and conquer. Problem is a decision plus subproblems plus a combination. I'm going to say the solution to a problem is some decision plus the solution to subproblems plus some form of combination. This is very conceptual. The pluses here have nothing to do with addition. So in general, in divide and conquer, and I wanted to put those two examples up so we can think about them. There is some decision being made. It results into subproblems that are usually on the same form as the original problem, right? Once I pick an item, I still have a knapsack, I still have a bunch of items, I still have constraints, all of that. If I solve the subproblem, so by solution I mean solve the subproblems, there is a way to combine those solutions to get back the original problem solution. Now I may have written this differently last time, and different books will say it differently. It doesn't matter how you write it. It's this principle, that's how divide and conquer method work. And so what is this decision in here? In this example? Is the greedy choice, right? In greedy problems, decision is greedy choice. What is the subproblem? Once I make that decision, what is the subproblem in this case? I would have a different time remaining, right? So I start with my big time range. Once I make a decision, I don't have that time anymore because I put an activity in it. I'll have only the remaining time after that activity, right? And the activities are the ones that are not blocked by that one. Should I write this down? I mean, does it make sense? Hands up, who's with me? Hands up so I can see them, please. Okay? How about in here? What's the decision? There was a greedy decision, right? What was the greedy choice here? Pick QI, the minimum between C and WI, that I has to be the arg max. We are maximizing. Which item did we pick? The one that has the highest value per weight, right? It says, take that ratio, take the maximum, and then pick either as much as you can fit in a knapsack, or take everything that's in the store. So that's the greedy choice is this decision here. The remaining problem would be, so the subproblem would be what? If I do that choice, what would be remaining problem? Z minus QI, that's the capacity of my new knapsack. And then all the items I have are what? Everybody's the same, W1, W2, except WI, which is WI minus QI, and then WI plus 1. That's the same. And the values are still V1, V2. There is a value here that you guys can compute at home. What's the value remaining for that one? And then the values. So this is my subproblem, which is the same exact form as the original, just smaller somehow. The knapsack got smaller, but it's the same problem. Okay? So in both those cases, this is the greedy. So for greedy, this is the greedy choice. The subproblem are determined by the greedy choice, and there are not many, usually one or two. In both these cases, how many subproblems I have? One. I make a decision, the remaining one is one problem. If I have some sort of tree, I make a decision, I may have two subproblems now. Right? Not many, and solutions are all necessary. So I can't go around by not solving those subproblems. And the combination, this is pure engineering. It has to do with how do we put back the solution from what we have. In those cases, there's no need for a combination step, right? If I keep going with this algorithm, I'm going to end up with the best optimal knapsack. If I could go with activities, I'm going to get with the maximum set activities. I don't have to. Combination just happens by the way I'm doing the algorithm. But in some cases, I may have to choose a max between two things, for example. Okay. In dynamic programming, decision here depends, so this is a decision, depends on subproblem solutions. There are many subproblems. Some not necessary. And the combination determines which subproblems we need. It's not sometimes a clear distinction between the decision and the combination. Sometimes there is a blur of which one is decision, which is combination. The main difference effect is that in dynamic programming, I have to solve the subproblems before I make a decision. In greedy, very often, I can make the decision before I solve the subproblems. Note that in those problems, in both of them, I made a decision what item to pick or what activity to pick without knowing what other activities will be chosen later. Right? I didn't know the solution to the subproblem. I didn't know how is this knapsack going to get filled, the remaining one. I didn't know what activities or how many I'm going to select. I say, choose this one, move on. In dynamic programming, we can't do that. In dynamic programming, we have to kind of trial and error. You have to solve the subproblems and only then figure out how to combine them or which to combine. Okay. So that problem was solved last time completely. For this problem, what do we need to do? You guys gonna go home and fix the pseudocode, right? Figure out how to implement this in n log n. But we need to prove that the greedy choice is correct. So we said there's two kind of proofs. If it's greedy, we have to prove that the greedy choice is correct. If we decide it's not greedy, out of the scope for this class, would require some sort of proof that no greedy method works. So if you come up with a dynamic programming solution, there'll be a question, why can't this solve by greedy? You don't have to prove that in this class, and some of these proofs are impossible hard. But you're gonna lose points if you're wrong. If you do solve something with dynamic programming, and there was a better, more efficient greedy solution, while the proof is not necessary, we are asking you to find that better solution. So we need to prove in this case that the greedy choice is correct. Let's do that really quick before we move on. How does one prove that in activity selection problem, greedy choice is correct? So what do we have to say here? We need to say that the optimal solution, this is optimal solution, can be obtained. Remember, optimal solution is not unique. That should be obvious in this case. If I have 20 activities, the maximum possible to schedule might be 5. But which 5 is not a unique thing, right? I can schedule those 5 or those 5 or those 5. So the solution is not unique. All those solutions will have the maximum number of activities. So an optimal solution can be obtained by my greedy choice plus a solution to a subproblem, to the remaining subproblem. So that's what we want to prove. That if we make this choice, and somebody obtains somehow an optimal solution here. We don't have to explain how to do this, right? We have to say, so how do I write that down for you guys to nail it in your mind? We don't have to solve this. For the proof. What we have to say is, my greedy choice, plus if somebody solves this problem somehow, optimally, that will create an optimal solution for my problem. So in other words, once I make that choice, if somebody can, me or somebody else can solve this problem, I didn't lose anything. If the number of activities obtainable maximum was 5, and I make this decision to choose that particular activity, then somebody should be able to obtain 4 activities in here. Right? And then the greedy choice will always work with the subproblem, because the subproblem is decided by the greedy choice, right? So that's one way to think about it. The other way to think about it is by induction. The statement will be, I think that's harder in this case, but it's a more general technique if you want to think about induction. It's saying that if the optimal solution, if for this problem, say the optimal solution is T activities. Right? That is, we don't know who T is, but there is a maximum T that's obtainable. After K greedy choices, for any K, so for any K smaller than T, after K greedy choices, the optimal solution for the remaining subproblem, it's only one subproblem, right? So that's saying after I make K greedy choices, this is T minus K. So this would be a statement I prove by induction by K. For K equals 0, it's obvious, right? After in the beginning when I made no greedy choice, the optimal solution has size T. There are T activities that can be scheduled. That's from the statement. Once I make one choice, the remaining thing must have T minus 1 and keep going, right? So I could try to prove this by induction. I think I'm going to prove this one here. But depending how the problem looks like, one might be easier than another. It also might have to do with the way you think about this. Everybody represents this problem in their head somehow. And sometimes the way you feel comfortable, the way you see the problem might be easier for you than for the other person. So don't neglect that. If I say that seems easier to me, doesn't mean it has to be the easiest for you. So how do we do this? If I make a choice, so my choice is select some activity I that has, what was the I equal arg mean of F, right? Because I selected the earliest finishing time. So why is it that, now what do I have to do? I have to say, that's my greedy choice. I'm assuming somebody can do this optimally. What I want, so again, I don't have to solve this. I'm saying if you solve this optimally and I put together my choice on top of it, then that has to be an optimal solution for my problem. So I'm gonna leave this induction for some other time, maybe some other problems. So what do I want to say here? I selected this activity I, and we had this sorted, right? So what's the remaining subproblem? What is this?
The time.
This was obtained by, first of all, the ones before, the way we thought of the algorithm, they're done, right? We don't have to go back to those. And then I eliminated every activity that was overlapping. So any activity that was overlapping, like that, is now gone. Doesn't exist. The only ones existing are after this, say, time t, right, in here. So there might be some activities, they also sorted, right, by the finishing time. This is the subproblem. So what this statement is saying, if somebody solves this, meaning finds the most number of activities that can be scheduled after this time, because now this is also an invalid time. This part of the time is gone. But from here forward, there's a new problem, the subproblem remaining. If somebody solved this optimally, what I want to say, if that suppose the optimal solution here has size, I don't know, pick a letter, G. Again, I don't have to solve that. If that has size G, what would be the overall solution? G plus 1. So if this has size G, I need to show that the optimal solution is exactly G plus 1. Because my solution would be G plus 1, right? If this has size 20 activities, that together with this one that I just chose will be 21. Okay? In fact, I only have to show one thing, right? What I have to show is that there is no optimal solution. The optimal solution doesn't have G plus 2 or more activities, because I can't obtain G plus 2. If I pick this one and the maximum schedule here is G, I am to G plus 1, and if maximum was G plus 2, I will not achieve it, for sure. So how do I do that? Yes?
Maybe we try to prove that in the window that we select from SI to FI, in this time window, you can select at max one activity which starts and ends in this way.
Right, that's true, but then how do we put it back into the right general statement? Of course, in every time window, that if things are overlapping, you can only select one of them. And that's what makes it possible to solve it greedy. But the question is why that mechanism can be proved in general.
So if we don't choose the first choice, the next choice will it will start after that choice, right? So the size of the subproblem that we are dealing with decreases. So it cannot be
Right, that's the same. It's the mechanism you're describing is correct. The argument is correct. Why this one's good? Intuitively, it leaves as much time left as possible. No other activity can leave that much time. But how do you formalize this into a proof? That's the question. I think we all understand why this greedy choice is good. You guys are trying to argue that this is a correct greedy choice. But how do we actually put it down rigorously? I think the right way to think is to say, give me an optimal solution. Like, since we are proving stuff here, we're not writing the code now. We're not implementing an algorithm. We are just proving stuff. We can assume that we see this optimal solution, or somebody give it to me, right? Or there is an optimal solution, right? There's a distinction between I'm assuming I know what's optimal when I do a solution, a proof, which is correct, versus I'm assuming what's optimal when I'm trying to write the algorithm, which is incorrect, because the algorithm is supposed to find that optimal, right? So the right way to think about this is to say, take the optimal solution. I'm going to say this optimal solution is literally a bunch of activities, right? I1, I2, some many, T of them. And I'm going to assume whatever vector of activities is in here, the optimal solution, doesn't matter how it's obtained, I can sort it by the finishing time. So I cannot say the finishing time of those i's is sorted, because that's not part of the solution to sort it. I sort it. So if somebody, God comes down to earth and says, here's your solution, that's the optimal. Okay? I take the activities and I sort their finishing times. And now I say, either the first finishing time is the same like mine, in which case there's not much to prove, right? So there's some few cases, right? Let's say if the optimal Fi1 is my greedy choice, so that's case 1. Then what? If this, I look at this optimal solution, I know this is a difficult thing. Most students have problem with this, even at the PhD level. They not problem with the mathematical reasoning. The problem is, how can I look at the optimal solution? Like, how do I get it? Where is it from? Who's going to give it to me? I understand that. In mathematics, people do that all the time, right? In algorithms, when you solve a computer science problem, you can't just say, look at the solution. Like, I don't have the solution. If I had the solution, I'd be done, right? You have to wrap your mind about this for the purpose of proofs only, okay? Proving only. It's not about writing the code. It's about just proving the code is correct. We look at the optimal solution. There is one, okay? We kind of assume we have it in our hand already, just for the purpose of the proof. So we say, okay, I can sort the finishing times. I look at the first time. Is it the same activity, the one I select? Suppose it is. Why is this and this correct? Well, if I pick the greedy choice same as this guy, Fi1, clearly, in that case, t minus 1, this number of activities have to be equal to g, right? Meaning, there is an optimal remaining part that does those things, right? Actually, let's go more deeply into that. Is it possible that this optimal solution G to be smaller than t minus 1? Suppose I choose this activity, and then how do I prove this? I'm going to say it's not possible for G to be either smaller or bigger than t minus 1. Here's why. Suppose this G for the optimal remaining subproblem. Remember, this subproblem is once I take out that activity. I have no control over how this solution was obtained. Maybe this solution doesn't use subproblems. It's God, so it does whatever it wants, right? When I say I have the optimal solution in my hand, I'm not assuming a way to obtain it. I'm just saying somebody gives me the answer. They may not use subproblems to get that answer. Maybe they try all possibilities and just evaluate the best one, brute force. But the subproblem is generated by me. Greedy choice dictates what the subproblem is, right? So I pick the first one. I'm in the case where they're the same choice. I say this subproblem cannot possibly generate more than t minus 1 activities. Because if this generates more than t minus 1 activities, if G is bigger than t minus 1, then God was wrong, right? If this valid solution to my greedy choice generates more than the remaining t minus 1, this is not an optimal solution. Ends up to suit me. Good. Why now G cannot be smaller? So why is it that if this is the optimal solution, that's a given. God is right, okay? If this is the optimal solution, why is it that this has to obtain it? I'm assuming whoever solved this problem solves it correctly. Like, I'm not saying I know how to solve it. When I say optimal solution, I mean there is a way to obtain optimal solution. Clearly, there is a solution that has t minus 1 activities, right? All these t minus 1 activities are a solution to my subproblem or not? They are because they're valid, right? They can be blocked by Fi1. So if somebody solved that subproblem, should be able to obtain at least t minus 1 activities because that's a solution for the subproblem, right? So what I'm saying is fi2 all the way to fit, this, it's a valid solution to my subproblem. My subproblem because I was the one making the greedy choice. So in essence, I say, if this is the case, t minus 1 must be equal g, which proves the theorem, right? It says like, okay, the whatever number of activities are obtained here, plus 1, is going to be the optimal solution. What happens if that's not the case? If, so that's case 2. How can this f be positioned to my f? So if they're not the same activity, if they're the same, they're the same. But if they're not the same, how is this f positioned to this f? So the optimal solution, this is what case? Optimal solution fi1 is not my greedy choice. My greedy choice is this I, right? So we don't choose the same activity. I look at God's solution. I look at the earliest finishing time in that solution. I look at my choice. It's not the same activity. But which one has to have an earliest finishing time? Between those two, if they're not the same, one is definitely the smaller one. Which one?
The greedy one.
The greedy one, because that's how it's chosen. If this was valid, I could have chosen it too. It was available for me too, but I didn't choose it. Why? Because my f has to be smaller than optimal solution f I want, right? That's how I choose it. That was available, but I choose one that's smaller. Okay, so what's the situation between me and God? Here's the situation. I chose an activity that ends here. God's solution, which is optimal, chooses a different activity that ends optimal. This is greedy choice, my greedy choice, right? And this is optimal solution fi1. And then, of course, after this choice, there is some more activities in the solution, right? There is maybe one here and one here and so on and so forth. The optimal solution contains more activities. These are the fi2, fi3 up to fit, right? That's possible. There's no contradiction in here. But I still want to prove my theorem. I still want to prove that if this has g things in it, assuming it's solved correctly, the actual optimal solution has g things, plus 1 must be equal to t. So this is my choice, this activity right here, and this is the actual solution. How do I prove this? Yes.
The time range left after our the subproblem left after our greedy choice is bigger than the optimal solution's subproblem range. So eventually whoever solved it, the subproblem for us, would have, if given the optimal solution, had more time to find that answer. So it has to be correct.
Right. But how do we say it nice, like mathematically settled? Here's what I'm going to propose. I'm going to say, ignoring this one, ignoring the first one, I look at this part. So I look at the optimal solution as a set of activities, minus the first activity. That was I1 in optimal solution. So I'm saying, take that first one out from the optimal solution, God solution. I say this set is valid for my subproblem. So I say this particular set is a valid solution for my subproblem. I think that's what he was saying I give it my available time from here, right? This is where my available time for the subproblem starts. While these activities, except the first one, all start from here. So I can, if these activities can be scheduled starting at this time, they can certainly be scheduled starting at this time. So they form a valid solution for my subproblem, which means my optimal solution G has to have at least that many activities. Right? Because this is an answer, the optimal answer is bigger than any answer, right? Bigger or equal to any answer. I think that proves the theorem. This is called an exchange argument. The way you formalize this is saying, look, I take God's optimal solution and I swap the first activity with mine. So I take this one out and I put mine in instead. Is now still a valid solution? Yeah, because if everything started after this line, by replacing that activity, it's still valid, nothing overlaps. How many, did I change the number of activities in the solution? No. So if that was optimal, this is optimal too, which proves that my greedy choice plus the subproblem has the same number of activities max as the optimal solution. In this class, we do not emphasize rigorosity. So rigorosity is important, but it's a second thing for us in here. In this class, we emphasize correctness of thinking. So if you go around the bush with all kinds of arguments that are correct and you are able to explain them even in English, even without formalization, you should get the points in midterm, final, homework, so on and so forth. I'm not asking for rigorosity or formality mathematically. I'm asking for a clean thinking. You're going to lose most points when your argument is incorrect. But you're not going to lose that many points if you write it in words, except for math. Now, math is better. If you could write it nice and easy, I prefer that as opposed to novels of everything came to mind at that moment, right? So there are ways to do this more formally, and I think there's the book, there is all kinds of Wikipedia documents. I just put one more note about greedy online. I think that's important once you understand the inside mechanism. Right? That's the hard part, understanding what's going on. Then you have to learn the formalism. Okay, so I think we're gonna have to stick with this equation a little bit more in general. But by now we solved two problems. One is the fractional knapsack. The other one is activity selection problem. So I want to go back here and discuss a little bit divide and conquer. That's true for both greedy and dynamic programming. This idea, picking the optimal solution and looking into it for the purpose of a proof, it's essential in divide and conquer. It's not just a proof technique. This is a way to figure out what you want to do. Now, keep in mind that you don't have the optimal solution when you write your code, obviously. But that's how you should always start a divide and conquering problem. Always. If you think it's divide and conquer, if it feels that way, always think about the following question. So this is the fundamental question. Divide and conquer. What will optimal solution look like? So we should repeat this 100 times. Every time we see a problem, first question we ask, if somebody would give me an optimal solution, how would that look? What property will it have? Now, it doesn't mean I can, it's different, verifying or looking at a solution is much easier than coming up with a solution. That's the first thing you should ask. If somebody gives me a solution, what kind of property will it have? More specifically, what structure of subproblems? So I want to, this is an absolute fundamental thing for divide and conquer, an analysis of the optimal solution that we don't have. Emphasize, we don't have. So clearly this is on paper exercise. I can't start writing code assuming there's a solution that I obviously don't have. This is just thinking about it. Take this problem, or take that problem. The first thing we should ask is, if a solution comes along, how would that look? So I'm gonna look at this problem first here. I have the activities going here. If God comes down and says, okay, that's your solution, how would that solution look like? There's an activity, right? Another activity, right? Another activity, another small one here, another one here. Maybe there's one here, right? That's what the solution would look like. So what's the structure in here? In terms of optimal solution for subproblems. I'll say it the first time, you say it after. Anywhere you break this line, timeline, you can pick to break it between any activities. I mean, not cutting an activity in half between them, because they can't overlap, so I can pick a time in between. What? If I pick a time between any, I can pick this time, I can pick this time here, anytime. Or I can split it into 3 chunks if I want to. Then this optimal solution has to have a magic property. It's what?
Optimal for that section.
It's optimal for every section. This is a magic property that all divide and conquer problems have. If they don't have it, it's not divide and conquer, it's brute force. If the solution as presented to you already done, this is not you find the solution is given to you, doesn't have this optimal per chunks, per subproblem, per sections, it means it cannot be solved by divide and conquer. You need brute force, you need to try all possibilities and see which one works. There's some problems, at least so far, after 50, 60 years of computer science, there are still some problems that we don't know how to solve any better than triangle possibilities. Anybody familiar here with the 3-sat problem? What is it? Giving a set of conjunctions of 3 things, right? Which is A or B or C, literals, and that's not a conjunction, not B or C or D, and find an assignment of the Boolean to satisfy all conjunctions, right? Very simple problem, can be stated in terms of 3rd grade. We don't know how to solve that problem other than trying all possibilities and see if one of them works. Now, some people believe, most people, that there is no way to solve it with computer science. It's not like we don't know, it's just impossible. But might be possible with quantum computing, because quantum computing has a different feeling and structure than regular computing. Now, that's not proven. There's a theorem that says that kind of problem, 3-sat, it's hard enough that only brute force works. That's a very famous conjecture, not proven yet, and if you prove such a thing, you're instant famous and instant rich. Everybody knows that conjecture, how it's called? 3-sat, or any other problem like 3-sat, is not solvable efficiently. There's no efficient algorithm. The only way to solve it is to try all possibilities. How is that conjecture called? Close. P versus NP, right? P is not equal within V. That's a very famous computer science theoretical question. So I want to point out here at divide and conquer that there are some problems for which there is no divide and conquer, there is no efficient algorithm. That's because it doesn't have this magic property that when you split the optimal solution, that's given to you, okay? It's not the one you found, it's given. It doesn't split into optimal chunks. But clearly that happens with activities, right? If somebody gives you optimal solution, any time you pick, there's gotta be, the optimal solution has to be optimal left side, optimal right side. Why is that? Why, if I pick this time, the maximum number of activities here must be 2? Right? That's what optimal means for the left side. The 2 on the left side, that's the maximum. Why can't be 3 or 4 or 5?
Summation would not be the optimal.
If there will be 3 or 4 in here, I take those 2 out, I put those 3 in, or 4, how many there are, and I get a better solution overall, which contradicts the fact that the first one was optimal. Right? If this is optimal, and somebody says, no, no, I can fit 3 instead of those 2, well, then 3 plus the rest will give me more. How about the knapsack? How do I think? I want to think the same way in terms of this knapsack. I don't want to think of the algorithm. I want to think of the solution. How a solution look of the knapsack? When you're done, what is the solution? Take so much coffee, right? Q1. Take so much sugar, Q2. Take so much beans, Q3. And take so much flour, Q4. Right? A solution is simply those quantities, right? And it has to realize the maximum. And the sum of those things have to be smaller than Z. What property this solution has? Magic property. The divide and conquer property.
Optimal quantity.
Here's the quantities. This is Q1, right? This is Q2, this is Q3, and this is Q4. Maybe some of them are smaller than the others. There's not a uniform partition here. If I chop the knapsack at some point, I look at, here's what this person puts in the knapsack, the optimal solution. I look at the knapsack and say, chop it off. What?
So the remaining quantity can be filled optimally by those solutions.
Right, so how do I say this? The left side has to be optimal in what sense?
The remaining capacity of
So obviously the capacity is just going to be Z left here, whatever I chopped off. But is this an optimal? So I mean, it still has the magic property, but we have to do it carefully. I think if this is the order in which we pick the items, this one must be absolutely optimal for the first side. Because at this point I have available all the items. If my knapsack will be only up to here, this is the optimal way to do it. On the other side, Z right, this is not necessarily the optimum overall if I have all choices. This has to be the optimal if I don't have Q1 and Q2, right? So that's a little bit harder to think about, but still has this property. Again, if one of those wouldn't be optimal, there will be a better way to do it, and replacing that side with a better way, I get a better solution overall. This has to happen in every divide and conquer problem, greedy and dynamic programming. And we're going to make it a requirement that you write this down for every problem, greedy or dynamic programming. You have to write down. The property is not called magic property. It's called optimal solution structure. The book talks at length about this for both chapters, dynamic programming and greedy. The Corman book talks at length. It's kind of hard to parse that if you don't know it. Like if I explain to you and you do some problems first, then you can read the greedy chapter from the book. But if you start reading it without knowing what's about, it's very confusing. So this property has to do with solution, optimal solution, the one that I don't have. How does it break down into parts? And to be able to use dynamic programming, I have to be able to solve the parts and put it back together. That doesn't happen in 3-SAT. Take parts of 3-SAT, you solve them, say less conjunctions, right? Instead of n conjunctions, I do half, the other half. Now you can't combine the solutions. That just doesn't work. That's why we can't solve 3-SAT by divide and conquer. Okay? So that's one thing that's going to be very important, and as a formalism, it's going to be some points associated. Every problem, midterm homework, you have to first start with analysis of optimal solution structure, or some people call it optimal substructure of solution. It's the same thing, which has to do, again, assume that somebody gives you the solution. Don't bother solving it. If somebody gives the solution, what is the property of that solution? There's actually two things that you need to worry about there. Optimal solution structure. There's one that says an optimal solution is optimal for subproblems. That is, if I take the optimal solution, my knapsack, I break the knapsack, that part of the solution has to be optimal for that part of the knapsack. Take the time, or where did I have the, I have it here, it's a bunch of activities. I take the split, the optimal solution structure. If this is an optimal solution overall, when I split the time, that part of the solution before left has to be optimal, and that part on the right has to be optimal. That's what I'm saying here. Optimal solution is optimal for the parts. And part two, by solving, there is a way, there exists a combination. That's the engineering part of the solutions for the subproblems to get back, to give me back the optimal solution. So this one says that if there's optimal solution, the subproblems have that as optimal solution. And the other part says, okay, clearly this is a necessity, right? If I have this proven, then the subproblems have to be optimal, right? So I solve the subproblems. But there's got to be an engineering way now to take the solution for the subproblems and put it back together. I think we can find examples where this is true. In 3-SAT is true, for example, right? If I find an assignment that satisfies all the clauses, and I pick now only 5 clauses or half of the clauses, that assignment will satisfy those half of the clauses, right? The problem is I can't solve the subproblems, get this part of the 3-SAT solved, this part of the 3-SAT solved. I can't glue it back together. Right? So those are the two things that we need. The other thing I want to do before moving on here, very related to this. This part, this middle board here, is the core of our course. It's divide and conquering. That's written this way with the structure and with the table I'm going to draw here is the absolute main thing in this algorithms course. The one that's going to matter anyway after. You know, we're going to talk about fancy things that you may not need, but this one you're going to need for sure. So the other way to think about it is to draw a solution, optimal solution subproblem table. So let's do it for activities first. Here's for activities. Each cell is a problem in this table. So for activities, what are my parameters? What is the input to my problem? The input goes on the sides of the table. Could be a 2D table, 3D table, 1D table, depending on what input I have. What is my input in here? It's the activities. I'm going to call the activities as 1. one kind of input. So I'm going to say, here's a set of activities. So each column here is an activity set. Is that array with starting and finishing times. And what else is given in my table, in my input here? The time. The time is important because the time will change with every subproblem, right? Time is not a constant. This range 0 to max, every time I move to a subproblem, it's not 0 to max anymore, right? So this is the time range. Time range. That is some beginning to end, right? The reason I need this to be a dimension in my table is because every problem is going to modify, every subproblem is going to modify this time range. I wouldn't need here a constant, right? If there is some kind of constant that I use for my problems, the same constant all the time, like the number of dimensions is 3, I don't know, for some problem. That doesn't need to be part of my table. So what is in here? This is that problem. Given the time range, call it R, and the activity set, call it A. That's saying you need to solve the problem given those activities and given this time range. How do you find the optimal solution? What's important in this table is the dependency. The problem in this table is to figure out, if I want to solve this problem, what are the subproblems for it? Where are the subproblems? Right, there's other cells in here, right? Right? So, but some of them are possible subproblems. Maybe this is a subproblem of that. What would make it a subproblem? What does this need to be a subproblem? I think this set of activities, call it A1, this is A0. What that needs to happen? A1 needs to be a subset of A0, because otherwise it will be a subproblem. And the time range, R1, has to be inside R0 somehow, right? So R1 is included in R0 as an interval. So some people even put arrows to say, if you want to solve this problem, this is a subproblem. You need to solve this subproblem, this subproblem, this subproblem, and this subproblem. So there are 4 subproblems that needs to be solved. I'm not saying that's true for activities. I'm saying what you want to look at this table is, by solving this problem, what subproblems I need to solve. Why is that important? Is because to do it efficiently, for greedy it's obvious, but for dynamic programming it's not. You need to solve the subproblems in a certain order. In greedy, you can do it top-down because you can start with, what allows top-down for greedy? I start with the main problem. I can make the decision right away, right? That's the thing with greedy. And making a decision immediately dictates the subproblems I need to solve. So I won't waste any time by going top-down. I start with the problem, make a decision, immediately go into subproblems. Because those subproblems, or one subproblem, if it's only one, needs to be solved anyway. But in dynamic programming, it's not like this. In dynamic programming, if I go top-down, I'm going to end up solving, remember the Fibonacci first class? I'm going to solve the same subproblem many, many, many times. So to implement dynamic programming, much better off to say, forget the top-down. I'm going to solve all these subproblems in the table once. To do that, I need to know in what order to solve them, right? Because to solve this problem, I need to have already solved these other problems. So you can think like that for greedy, but for greedy it's not necessary, because for greedy there are no extra subproblems to be solved. However, I think it's a very important way to think about if you don't know how to solve the problem. Right? How does a problem depends on the subproblems. What would be the table for the what's the table for this? what would be, this is very similar, what would be on this axis? A set of items, right? Set of goods or items. And what's in here? The capacity of the knapsack. So this is saying, how do you solve the problem with that knapsack, with that set of items, right? In these problems, it's important to manage the dimensions carefully. So this activity selection problem, it's easier than the goods problem, the flour and coffee problem, because we can sort the activities in an easier way. So I sort them by the finishing time, and then those sets, like how many sets are total possible? If I say I have an activities, how many subsets I'm talking about? So it says activity set, but this is maybe a subset. So how many subsets are possible in there? I have n activities. I have n items. How many subsets of n items are there? 2 to the n, right? But obviously I don't want to put 2 to the n ticks on this axis here, right? That will create way too many subproblems. 2 to the n will be an exponential time algorithm. So I need to manage those activities. So instead of putting all sets, maybe I sort them by F1, F2, all the way to Fn. I sort them by the finishing time. And then I don't need to solve subsets that are not ordered by finishing time. Same thing in here. In here it's a little bit more difficult. In the greedy version of the problem, which is the one we did here, the reason it's greedy is because I can sort these goods. How did I sort them by? Ratio, right? So this is the biggest item, value by weight 1, value by weight 2, so on and so forth. In the discrete version that we're going to do next week, this doesn't work anymore. And then we have a problem with this axis. How do we represent all the subsets of items on that axis? We need to come up with something. We're going to talk about that next week. But in many of these problems, generally for greedy and dynamic programming, we need to draw this table. So the first two things I would do with any such problem, unless it's obvious I know the answer, I would first think of this. If somebody gives me the solution, how the solution looks. Once I see the solution, how it looks, I'm asking, can I make a greedy choice? Can I determine the subproblem with a choice early on? And then I would draw this table. I would say, okay, if you want to solve this problem, what subproblems do you need to solve? This is the same representation as this equation. Because answering greedy, say, okay, I can make a decision, is saying, I don't need to look at the solution of those subproblems. I could decide in advance which ones I need to solve. If I say, I don't know, it may be those 4, or it may be these other 3, depending on what the answer is. That immediately that's a dynamic programming problem. If you don't know which subproblems you need, because you need to see the answers first, then that means you can't be done greedy. So now, I want to ask you guys a few questions. So this is the main 2 problems that I want to show for greedy. I have another one that requires a little bit of graphs, something that you already know, undergraduate. But before I go there, I'm going to pose some problems so you guys can take a guess into are they greedy or dynamic programming. Okay. So here's one. I have, let me find a piece of board that. So divide and conquer problem. I have a wire, say of length L, and its price or its profit is fixed, say $1 per feet. So this is L feet of wire. You know how the wire comes in Home Depot in a roll of 50 feet or 100 feet? Say it costs $1 per feet. And any cut of size C results in C dollars. Like, no matter how I cut the wire, I can sell the parts for C dollars each. If I choose a 50 feet wire, I can cut it to 20 and sell that part. I can cut it in 25 or 20 or 50 or whatever, sell that part, right? How to cut it? Optimal way to cut. This is a trivial problem. No matter how you cut it, you're going to get L dollars back, right? Because every piece of the wire is worth exactly L dollars. Right? That's how, when you see in Home Depot, if you've been, some things that they sell by the feet, they have the cutting machine right there. You take how many feet you want of that pipe or rope, and they cut it, and you pay for the feet. They know that because the value is exactly $1 per foot, so some other customer will come later on, will take some other chunk of it. Now suppose the sellable parts are exactly 3 feet, like iPhone cables. Nobody wants a 3.5. Maybe people do, but I'm just for the example here. It's only 3 feet, 10 feet, or 20 feet. So L is a variable, but this is given. If I have a 4 feet piece or a 6 feet piece, I can't sell that. That happens a lot in construction because construction is standard. Take the door sizes. It's either 2 feet or 3 feet or 6 feet. So if your material is 4 and 5 feet, then you lost something because there's no door of that size. It happens a lot in standardization. So now I have an L wire, and the pieces that I can sell are 3 feet, 10 feet, and 20 feet, and the value for them is $3, $10, and $20. Can you cut this wire with a greedy choice? Can you look at the wire and say, the first piece I'm going to cut is a 20 feet piece, or 10 feet piece, or 3 feet piece? Can you make that decision? If I give you the L, I say L is 100. L can be anything. Can you use a greedy algorithm to say, the first piece you need to cut is that? Obviously, if you decide on the first piece, the remaining problem will be L minus what you have, cutting into, again, you want to maximize the value you get. The problem is to not remain with something that's a lot of extra that can't be solved. Right? Like suppose I cut my wire in such a way that I'm left with 2 feet. That's gone. That's useless. I can't sell it. Right? So can you do it greedily? Can you pick up sides of the wire by looking at these these are called denominations, and say the first piece you need to cut from the wire is a 10 feet. Obviously, if you're correct, there's no question that the greedy algorithm will go very well, right? We already said that. If you can make a greedy choice that's correct, writing the algorithm is nothing. You just keep going with the same greedy choice, right? And it's going to be efficient, right? If you can make a decision right away what to cut, that decision can be repeated and repeated for the subproblems until you guys following me here? If I can make a greedy choice, there's no question that the algorithm is going to be efficient and easy to write. The problem is, can you make a greedy choice? Can you decide on a greedy choice without solving subproblems? Which piece of the wire you need to cut? This is similar to say, I need to give change, the coin change problem, right? What is the United States denomination system? 1 cent. So coins is the same problem. Variant. This is still example number 1. 1 cent, what else they have in US? 5 cents. And the typical problem is I need to give change to somebody, right? Like 75 cents or even $1, and if I don't have dollar bills, some change. Can you decide without looking which coin you should give? Can you say, given the amount, L, of cents I need to give change, if, for example, here's a greedy algorithm. If 25 cents fit in L, give that. As long as you can give, what's the optimum, by the way, in here? This is a different objective. This objective in here is maximize value. The objective in here is minimum number of coins. So here's what I'm going to say. Obviously, if I give a bigger coin, I'm realizing something because I save some part of the problem with only one coin, right? 25 is definitely better than 5 fives. So there's a temptation here to say, that temptation does not exist here, right? If I cut 3 feet or 10 feet, as far as value per feet goes, is the same. The only problem here is not to remain with something that's not sellable. In here, there's a temptation to give the 25's coin first, right? And then I do that while the L is bigger than 25. When it's not, I move to tens. Would that be optimal? If you were to give change, and you, this is a greedy algorithm, right? I'm not solving some problems, I'm only checking, is 25 fits in? Give it. The problem will be what? L minus 25, and the same denominations. I'm assuming I have infinite number of coins. This would be an amazing, interesting problem if you only have that many pennies, and that many dimes, and that many quarters. That would be an amazing interview question, in my opinion. Hey, you don't have infinite number of quarters and pennies and all that. Just limited quantities. Maybe this one is infinite cents, so you can give the change. Well, now solve it. But let's not do that yet. So is that correct? Is that greedy algorithm correct? Give the best nomination you can and move on? Why? Because of these exact denominations. What if I change the denominations? Would that still be correct? If I say 1, 3 cents, what? 13 maybe? I don't know. If I change the denomination, is that still correct? Is that still that the best coin that fits in, give that as a change? What if I have a 13 and I could do it with a 6 and a 7? I have 6 and 7 here. I have a 7, so for, let's see, 6. If I have a 6, I could do 18 with 3 coins. So if L is 18, I could do 6 times 3 coins. But if I use the 13, the greedy choice, take the 13 out immediately of 18, now I can't use the 6s, and I have to use 5 cents. So the greedy choice doesn't work. So then I have another interview question. For what's the property of denominations that makes the greedy choice work?
Should add up to 1. Should add up to it.
What?
All the denominations should add up to it.
Multiples of features.
I don't think that's true. I think Fibonacci denominations, for example, have this greedy property. If your denominations are the Fibonacci numbers, you could give change optimally by giving the highest number that fits in, and they're not factors of each other. So what is the property that denomination must have to make sure the greedy is correct? That's a PhD level question. But what I want to point out, some denominations make it greedy work and some others do not. So how do you know what to do? So that's one problem. Another problem that I want to mention here is the problems that we're going to study after the spring break on graphs. There are many questions in graphs. So if I have a graph, my plan is not to introduce graphs right now. That's not what I'm trying to do here. But I'm sure you know this part already of graphs. These are my vertices. These are my edges. This is an undirected graph. It could be directed if the edges have a direction. Every edge has a weight. 1, 2, 100, 20, 50, 12, 5, 3, 31 maybe, 3, 2, 8, to so on and so forth, every situation. If I want to get from the start to the finish, there's the two nodes that I want. An obvious problem, theoretical and practical, is how to go from here to here in the shortest path, right? All the mapping problems, like Google Maps, Apple Maps, everybody solves short path problems, right? Is that greedy? Can I start from here and say, took the smallest road? No. Like if I have two edges, one is 1, one is 3, and one is 10, take the 1. No. Because it's the shortest one. No. I cannot do that. How about if I want the longest one? That's not a commonly, you know. If I want to get the longest way. That may happen when those are not costs, like when the person with the packet, you know, the salesman travels. Those are typically costs. It takes so many miles of gasoline or something so that you want the shortest because you want to be efficient. But sometimes there are benefits. To go from here to here, you click on all those rewards. So you want the biggest one. How about the longest path? Can I do that greedily? Take the biggest edge. No. Okay? So we're going to get there. We're not there yet, but we're going to get there. I want to put one more problem. Again, this is not, you don't have to study graphs right now because I mentioned these problems, because we're going to work on graphs. There's no graphs problem until after the spring break. But it's a very common problem to say, I have this graph, and I want a minimum spanning tree. What's a minimum spanning tree? It's a tree that's a subset of the edges. So it doesn't use all the edges in the graph, just some edges. The difference in a tree is that there's no cycles, right? So you can choose any edges you want, with condition that once I choose this and this and this, I can't choose this one because it forms a cycle. So it forms no cycle, but it's connected. The tree has to connect everybody, right? So it's connected, no cycles. And the minimum, so that's called a spanning tree. It connects everything and no cycles. Minimum refers to what? Is the minimum of the three edges total. So there are many spanning trees in here. There's many ways to connect everything with the tree that connects and doesn't have cycles. But we want the one, or the ones could be not unique. Maybe there's two trees that have the minimum. We want the one that realizes the minimum. So maybe that's this one here, and then there's a 2, and then there's a 3, and maybe there's another 1, and then it's 2, and maybe this, and so on and so forth. So only some edges that total sum to minimum. So I want to find a minimum spanning tree because that's how I can distribute efficiently things, right? Minimum spanning tree says that the distribution network is the fastest way to distribute to a lot of places. Can I do this with greedy? Can I find some algorithm that makes a decision? Decision is what edge to pick, right? What edge to include in the tree. What edge to pick in a greedy way. Is that possible? You can start anywhere. You can start with this node maybe, or this node, whatever you like. But the decision has to be greedy, meaning you pick an edge and say, that's in my tree for sure. I'm not going to change my mind about it. And then keep going somehow. Yes or no? What do you think about this problem? Can I do this with a greedy algorithm? I would say at the minimum is not as obvious as the shortest or longest path. Everybody can see that if you pick in the beginning a small edge, you want the shortest path. You may only have big edges after that, so you're stuck pretty bad. But in here it's not so clear. What if I pick the minimum global edge? Minimum, this one is a minimum, right? Can I guarantee somehow that that edge is in my minimum spanning tree, no matter what? I would say that's not an obvious thing to ask. I mean, there's not an obvious answer. Maybe that edge is guaranteed to be in my minimum spanning tree, maybe not. And then once I pick that one, can I pick another very small edge and say, that edge for sure is my spanning tree? This is the kind of problem you should think about. We're gonna do this. So I'm not asking you to come up with an algorithm. I'm rather asking you to try to do this. Can I break? If somebody gives me a spanning tree, so I don't ask you to code it up or to design the algorithm. I'm saying, can you analyze the solution? If somebody says, here's your spanning tree, does it have the property that the parts of it are optimal somehow? Definitely. Spanning trees are not a brute force problem. They have the optimal solution structure. The question is, can you break the thing before you solve the subproblems, or do you have to solve the subproblems to know where to break it? By the way, shortest paths, do they have the optimal solution problem? If I tell you this is the shortest path, and I break it into two parts, this must be a shortest path from here to here?
No.
Again, this is the shortest path, right?
Yes.
I break it here. Is it guaranteed that this part is shortest path? Can I have a different path shorter than this?
No.
Because I would exchange it, make it work, right? Same thing in here, right? So it clearly has this problem. The question is, do you know where to break it before you solve the subproblems? Can you somehow pick this point, says break it here, before you actually compute shortest path, right? So this tells you right away, this optimal solution analysis structure tells you that this is either grid or dynamic problem. It's solvable. It's not the kind of thing, try all paths and see which one is the smallest because there's nothing else I can do, like tree-sat. But shortest path, I don't think can be solved greedily. The minimum spanning trees, you can do the same analysis. If somebody gives you the tree, break it, does that have to be optimal for that part of the graph? And this has to be optimal for that part of the graph. Yes. Question is, can you decide how to break it before solving the subproblems? So we're gonna do this. It turns out minimum spanning trees are greedy, but you have to figure out why. One more question for you guys. What's a Hamiltonian path? Hamiltonian path, there's no edge weights here. So we don't have weights. Hamiltonian path, it's let's say cycle, to make it clear. It's a cycle that visits each vertex once. So that says, in my graph, there is some way of cycling to get all vertices and come back where I started. Can you find the Hamiltonian path in the graph? So I give you a graph. There's no edge weights. In that kind of graph, it's only just edges. Weights. Can you go through all vertices exactly once and start and end up where you started? Hamiltonian path. That's the kind of the USPS guy, right? Who starts at the USPS, wants to go through all houses, but doesn't kind of doesn't want to go twice. It's not exactly that. That's more like traveling salesman problem, right? But is that how do you do this? And there's a version of it that says traverse each edge once. It has a different name. All linear graphs. Finding one of these paths, I'm asking, is it divide and conquer first of all? If somebody tells you the solution, can you break it into parts? Assuming you see it. And then if that's true, tells you maybe there's a solution to these problems. But if you can't do the breaking, means it's kind of a brute force problem that you just have to try everything. Okay. So we have a greedy homework. And next week, dynamic programming. guys stop the camera? Okay, I think we started.
10:45 for the first time.